giving a talk about the results of a security assessment of the TCP and IP protocols. It's a project that I carried out on behalf of the UK Centre for the Protection of National Infrastructure during the last few years. This is the agenda for this presentation. I will start with an overview that will basically describe the state of affairs at the point this project was started, and I will describe the motivations for carrying out this project. Then I will provide or will discuss some of the results that we got from the security assessment of the IPv4 protocol. Then we will discuss some of the security implications of the TCP protocol, and finally I will try to provide some of the conclusions from this project that we carried out. As a kind of overview of why we started working on this project, let's say that most of you know, or probably all of you know, that during the last 20 years or so, many vulnerabilities were discovered in a number of TCP and IP implementations, and also a number of vulnerabilities were found in the protocols themselves. The documentation of these issues were, for the most part, documented in a number of vulnerability advisories issued by vendors and CSIRTs, and sometimes in other types of documents such as papers or websites and so on. One of the problems with the documentation of these issues is that many times the countermeasures that were proposed or suggested to deal with these issues were not really effective, or sometimes they were to some extent effective to mitigate these security issues, but they also have a negative impact on the interoperability of the protocols. I included here a reference to Mike Silversack's presentation at DSDCan 2006. I think he did the same presentation in 2005 or something at some other conference, because I think it's one of the first few, probably the first presentation on the negative implications of some of these countermeasures. And that aside, all the efforts in the security community about TCP and IP security never reflected into changes in the IETF specifications of these protocols, and sometimes not even in the implementations of these protocols. As a result of all this, it is very difficult to implement or produce a resilient implementation of TCP or IP from the IETF specifications. This is known to everybody working on a TCP IP stack. But it also is very difficult to spot the right advice from all the information that is available. I mean, it's not that it wasn't, that information on how to mitigate these issues wasn't available, but there's so much information available that it's really hard to spot what's the correct advice to mitigate these issues. The result of this state of affairs is that many times new implementations of the protocols have re-implemented bugs or vulnerabilities that had already been found in older implementations, and sometimes even new protocols have introduced mechanisms that had already been known to have a negative security properties. I'm just giving here an example that, for example, in IPv6, it included the routing header type 0 mechanism, which is basically the IPv6 version of IPv4 source routing. So I think it was only a couple of years ago that the IETF ended up deprecating this mechanism. I mean, it's weird, really. As a kind of overview to the project that I carried out on behalf of CPNI, the idea was to fill this gap, try to produce a set of documents that would serve as a roadmap to the security implications of TCP and IP. We tried to perform a thorough security assessment of both of these protocols, tried to spot all the information that was available, relevant papers, online documents, and so on, and from all that information try to provide the correct advice on what implementations should do. Our effort, we hope to produce a document that wouldn't be probably the final word on TCP and IP security, but rather that it would sort of trigger a discussion in the community, and we expected that as a result of the publication of this document, we would probably would have to update our documents in response to that feedback. Finally, we saw that in order to consider our project complete, we have to take the result of our project back to the IETF so that the relevant specifications could be updated where and if necessary. Well, the output of this project were two documents. The first one is Security Assessment of the Internet Protocol. It was released by the UK CPNI in July last year. And we also submitted an IETF version of this document, which has already been adopted by the IETF. So it means that at least the IETF will work on these issues and will publish something on the subject. When it comes to the security assessment of TCP, we published the result of our project earlier this year. This slide provides the URLs so that you can get these two documents. And we also publish an IETF ID version of this document that the DCPM working group of the IETF is currently discussing as to whether it should be adopted as a working group item or not. I think it's going to be discussed at the next meeting that is going to be held in Stockholm in a couple of weeks. Well, of course, these two documents account for something like 200 pages, and it would be almost impossible to discuss all that stuff, present all that stuff in 45 minutes. What I tried to do is to select some of the topics that were contained in both of these papers so that you could get a feeling of the type of work that we did. It's interesting to know that in some cases, it's not that the security implications of or the vulnerabilities that we discuss in these papers are new, but sometimes what is new is the countermeasures to mitigate them. This is sometimes a little bit frustrating because usually in the security community, the only thing that matters is whether you discover a new vulnerability, but it doesn't really matter whether you fix something that was there, but nobody fixed it. So in the conclusions that I will provide at the end of this presentation, well, one of the things that I mentioned is that sometimes working on this type of stuff is a little bit unfair, because just for the fact that you're working on TCP and IP, that means that, well, all protocols, nothing to be done there, so nobody will sometimes care to even read the work that you did. In the case of IPv4, the only field or mechanism that I will discuss is the security implications of the IPv4 identification field. And the reason for which I selected this particular field is because even during the last few years, there has been a little bit of discussion on how to set this field. And even in systems such as OpenBSD, it was found that they were setting this field in the wrong way. So as a kind of introduction or overview of what the identification field is about, the IP identification field is used for the fragmentation and reassembly mechanism in IP. Basically, the idea is that with the tuple, source address, destination address, protocol, and identification, you will be able to identify a set of fragments that correspond to the same additional packet, so that the system receiving those fragments can know which fragments have to be reassembled together, right? As a result of this, it should be clear that you cannot reuse a specific tuple while it is already being used to identify another set of fragments. In the event that you did that, that is that you select an identification value that is already in use, well, chances are that both of those packets could get fragmented, and the system receiving them could end up reassembling those fragments in a mixed way, right? So the result of the reassembly process would be wrong, and the packets would most likely be discarded at some point or another. For example, the wrong fragments could be reassembled together, and then when for example, the TCP checksum is performed, of course it would fail and the packet would end up being dropped. When this type of scenario happens, we say that an IP ID collision has occurred. That is that you have reused an IP ID value like too frequently. In order to avoid these interoperability problems, what most stacks have done in the past is to simply select or set the IP ID value from a global counter. This global counter basically is incremented by once for each packet that is sent, right? So the idea behind this policy is that you don't want to reuse a specific ID value before you have already used all the other values in that 16-bit long range, right? This is okay from an interoperability point of view, because it leads to a low IP/ID reuse frequency. But of course, as you can imagine, it will lead to predictable IP/ID values that could be exploited by an attacker to perform a number of things. If a global counter is used to select or set the IP/ID value, an attacker could, for example, count the number of systems behind an NAT. This functionality is already implemented, for example, in tools. I think it was tools such as Nmap or HPing. It can also be used to infer the packet transmission rate of a remote system. Of course, if the target system, you know that the target system is setting the IP/ID in an incremental way, that is, incrementing that field by 1 for each outgoing packet, then I can get one packet from that system, then get another packet from that system, and I will subtract those two IP/ID values, and of course I can tell how many packets that system sent in the meantime. And another thing that you can do with the with predictable IP/ID values is to perform a stealth port scanning. This is sort of related to the second bullet. The first of these issues was discovered, I think, for the first time by Stephen Bellovin in some paper. I don't know if it was published on in KCA or which journal. And the second and third bullets, I think, were discovered, or at least first publicly discussed by Salvatore Sanfilippo, the guy that produced the HPing tool. Well, of course, in order to mitigate these security implications of the identification field, you don't want to have predictable IP/ID values. That's obvious, right? However, it has always been assumed that you couldn't really randomize the IP/ID value because, well, probabilistically speaking, that of randomizing the IP/ID value could lead to collisions, right? Chances are that that you will end up reusing an IP/ID value like too frequently. Some systems, for example, such as OpenBSD, at some point try to produce some randomization schemes that, well, would obfuscate the IP/ID value, but would also prevent IP/ID values from being reused too frequently. However, years later, it was found that those algorithms that they were using actually would still lead to predictable sequences. You may read, there's a really good research by Amit Klein that I think it was published a couple of years ago, in which he discussed, well, the predictability of the algorithm used I think, by OpenBSD to set the IP/ID field and also to set the DNS transaction IDs. I think they were using the same algorithm for both things. So what we try to do here is to analyze the behavior or the characteristics of connection-oriented and connection-less transport protocols and try to figure out if there was a proper way to set the IP/ID field. So let's think a little bit about connection-oriented transport protocols. An example of this type of protocols, or maybe the trivial example would be TCP, but other protocols such as SCTP would be, the analysis for a protocol such as SCTP would be the same. Most of these protocols, if not all, they implement some mechanism for the discovery of the PAN-MTU, and of course the motivation for PAN-MTU discovery is that the performance implications of IP fragmentation have been known for more than 20 years, okay? And another thing to consider that I don't think has been so widely discussed is that if you think about the current bandwidth availability of today's networks, and you think that, and you consider that the IP/ID field is 16-bit long, you cannot really rely on IP fragmentation regardless of which specific algorithm you use to set the IP/ID field. I mean, the IP/ID field for today's network is too short, okay? In the case of IPv6, the state of affairs changes a little bit because I think they use something like 32 bits for the IP/ID, so things are a little bit better in that respect. As a result of these considerations, we think that you shouldn't really rely on IP fragmentation. So what you should do is to implement some kind of PAN-MTU discovery mechanism, not rely on fragmentation, and set the IP ID value to a random value for each outgoing packet. So let's now talk a little bit about connectionless transport protocols. The trivial example would be UDP in this case. These protocols typically lack of packet sequencing, flow control, and reliability mechanisms. Probably the only thing that UDP does is provide a checksum and also introduce the idea of port numbers so that packets can be delivered to different applications, of course. And the scenarios in which these protocols are used, or the applications the applications that use this type of protocols, to some extent they assume that packet reordering is unlikely, or that is not that important. They also assume that the data transfer rates will be low enough, or that the total amount of data that is going to be transferred will be small, that flow control will not be necessary. And they also assume to some extent that packet loss is unlikely, or that is not important. Of course, this is related to the considerations that we made above. For example, if packet loss were important or was very likely, well, it's you could say that the transport protocol should be implementing some kind of reliability mechanism, or that you should be using something else. Okay. As a result of these considerations, we think that implementations should set the IP ID value to a random value too, in the case that IP packets are encapsulating a connectionless transport protocol. In the event that an application was concerned about this policy, my idea is that those applications should probably be using connection-oriented protocols such as TCP. Well, the IP ID field is the only security aspect of IP before that I will discuss in this presentation, and we will now move to TCP that has a number of issues that are more important, I think. Before starting the discussion of specific security aspects of TCP, I will provide a really brief overview of some key TCP mechanisms on which the rest of this presentation rely on. The first of these mechanisms is the connection establishment mechanism, or widely known as the three-way handshake. It involves, of course, the exchange of 3 segments, and once that segment exchange is complete, the connection will end up in the established state in both endpoints, and from then on the data transfer can begin. The second of the mechanisms that I will be discussing is the connection termination phase. It usually involves the exchange of 4 or 3 segments. And what's important from this slide is that once this segment exchange is complete, one of the endpoints ends up in the closest state, which is of course fictional because that state doesn't really exist. And the other endpoint, the one that performed the active close, or the one that initiated the connection termination phase, will end up in the time wait state. That state lasts for twice, or in theory lasts for twice the maximum segment lifetime, which in theory should be something like 4 minutes. I'm saying in theory because that's what the specification says, but as it happens with most of the TCP and IP stuff, the IETF specifications are irrelevant. I mean, that's weird to say, but they are irrelevant. So let's now revise what could happen during the connection establishment phase if, when you try to establish a new connection with some remote endpoint, there is still a connection with the same connection ID, that is with the same source address, destination address, source port, and destination port, that is in the time wait state. Well, the specific segment exchange that will take place will depend on the specific specification that TCP is implementing. If that TCP implementation follows RFC 793, the segment exchange that will take place is the one on the left. That basically means that the connection request will be aborted. You can see that in response to the incoming SYN segment, host B is responding with an acknowledgement that contains a sequence number that does not refer to the sequence number in the incoming SYN. So that results in host A sending a reset segment. This was known like 20 years ago as time wait assassination, because that basically means that host B will remove that connection that was in the time wait state. Of course, there is a purpose in the time wait state. and it is undesirable for the time-wave state to be removed in this scenario. In response to this, RFC 1337 was published. I think the title of the document was Time-Wave Assassination Hazards. Basically, that RFC discussed the problems that could arise as a result of time-wave assassination. And the only recommendation in that document was that if you receive an incoming segment while there was a connection in the time-wave state, what you had to do is to ignore the incoming segment. So in this case, on the figure on the right hand, you can see that the incoming segments are ignored, are dropped, silently dropped, and thus, as a result, chances are that the connection will time out. I mean, your connection request, the new connection request, will time out. In all of these two cases, we can see that the new connection request will fail, and of course this is undesirable. Okay? In the first case, because the connection is reset at once, and in the second case, because the incoming things are ignored, and thus chances are that the connection request will simply time out. This means that the collision of connection IDs, that is that of reusing a specific connection ID, source address, source port, destination port, too quickly, is something that you should try to avoid to the extent that is possible. If you don't do it, chances are that new connections may fail. So this is the overview that I have provided on TCP, because many of the following slides will rely on these 3 slides that I have just discussed. So let's talk about a little bit about port numbers. This slide could have been entitled Port Randomization, but many of us think that what you really want is not really port randomization, but port obfuscation. That is to produce or to set the ephemeral ports in such a way that is not predictable by an off-path attacker, not really to randomize that value. And an interesting thing with port randomization or port obfuscation is that this has been discussed for many years. And what's funny is that we published a paper on the subject. I think it was the first version of our IB. We published that in 2005 or 2006. And I received an email from a CSERT, I think it was last year, a couple of years ago, mentioning that, they had found our paper so useful to deal with the Kaminsky attacks on DNS, and they were sending our paper as secret information to vendors, and that paper had been available online for 5 or 6 years. So people were talking about port randomization as the proper way to deal with all these issues, as port randomization was magic that had been unknown previously. But actually, this is something that some systems, for example, such as OpenBSD, had introduced in their stack for quite a few years now. So when a system wants to establish a connection with the remote system, an outgoing connection, it will have to select an ephemeral port. It doesn't really matter which specific value that system picks, as long as the resulting connection ID is unique. Of course, the set of source address, source port, and destination port identifies a specific connection. And of course, it makes sense that you cannot reuse that value for or that you cannot use that value at the same time for 2 different connections. Okay. So let's just say that the system selects an ephemeral port, and right after that, what the system is going to do is to try to figure out whether that value was already in use at the local system. That is of course very easy. You can just have a look at all of the TCPs that you have in your system, and in the event that connection ID was already in use, what you do is simple. You just pick some other port and continue trying until you can come up with a connection ID that is not in use. Problem happens when that specific connection ID is not in use in your system, but in a remote system. Put another way, the problem happens when you select an ephemeral port, and some remote system has a TCP connection, for example, in the time-wave state. I mean, it's trivial to detect that that connection ID is in use in your system, but it's very difficult to detect that the same connection ID is in use at a remote system. Of course, if you were to select an ephemeral port and that ephemeral port would result in a connection ID that was already in use, a collision of connection IDs would occur, and this could this could lead to the scenario that I was describing in the overview, in which you send a SYN segment to a remote system, and that system either causes the connection request to be reset, or it simply drops or silently drops your connection request. That is, of course, undesirable and leads to connection failures. The way in which most systems have traditionally avoided these collisions of connection IDs is to select the ephemeral port from a global counter. This is the same approach that was taken for setting the IP ID value. Same thing. You don't want to reuse these values too quickly. So what you do is you just use a global counter, and the idea is that you don't want to reuse a specific value before all the other values in the ephemeral port range have been used. Okay. This makes sense from an interoperability point of view. This is the way in which most stacks have worked for the last, well, all the time that you can think of. However, of course, this leads to predictable port numbers. The security implications of predictable TCP port numbers are obvious. Basically, if an attacker wants to perform an attack against a TCP connection, the attacker has to be able to identify the connection to be attacked. So in order to do that, he needs to know the source address, destination address, or, well, client-side IP address and port, and server-side IP address and port. Of these 4 values, the only one that to some extent you can pick in whatever way you want is, of course, the client-side port number. So many of you might think that probably the best way to deal with these issues is to simply randomize the TCP ephemeral port. And that's actually what some systems have done in the past. For example, OpenBSD and at some point FreeBSD, they introduced simple randomization for their port numbers. The problem is that if you are running 2 systems in a specific network environment in which one of the systems is establishing connections with a specific endpoint at a very high rate, think about, for example, FTP, right? One system downloading many files from an FTP server. At some point, it's very likely that collisions will occur. And actually, this is the problem that FreeBSD faced when they introduced port randomization in their stack. In one of their releases, they introduced port randomization, and they were getting complaints from the users that, well, now some connections were failing that before they were not failing. So what, for example, FreeBSD did is they sort of measured the connection establishment rate. So when the connection rate is higher than something, I don't recall the exact value, they basically disable port randomization. Other systems, to the extent that I know, I think OpenBSD, for example, they continue using the trivial port randomization scheme. So let's think about what would be the characteristics of good port obfuscation scheme. Well, the most obvious one is that it should be able to obfuscate the TCP port number. That's the whole reason for trying to randomize or obfuscate the ephemeral port. The second of the characteristics is that it should avoid the quick reuse of a specific ephemeral port, or, well, put another way, the quick reuse of a connection ID. This is, of course, to avoid the interoperability problems that I was mentioning. And as a third characteristic, but of course this third one is trivial to implement, is that it should avoid the use of port numbers that are needed for specific applications. You don't want to use port number 80 or 8080 for an ephemeral port, because that port could need to be used for some specific application. A few years ago, Michael Larsen and me, we published an internet draft on port randomization. That's the title of the draft. That at that point in time was describing a single algorithm for randomizing or obfuscating the TCP ephemeral port. Right now, and as a result of the IETF process, the same draft discusses something like 6 different randomization schemes. And we basically don't really recommend in that document to implement any specific algorithm, because, well, you know, that's how consensus works. You have to put whatever ideas anybody has inside the document so that everybody's happy, okay? The specific scheme that we really recommend is a randomization scheme or an obfuscation scheme that is very, very, very similar to the scheme proposed by Steven Belovin something like 10 years ago for the selection of the TCP ISNs. basically what this equation tries to show is that port numbers will be selected as a result of adding a counter, a global counter, and the result of a hash function that will be processed, taking as parameters the local IP address, the remote IP address, the remote port, and the secret key. Of course, you cannot use the whole connection ID. You cannot use the local port because that's, of course, what you're trying to get, right? As long as the hash function is good and as the secret key is secret, the idea is that this equation will separate the port number space that is used to connect to different endpoints. This scheme has been found to have better interoperability problems than other randomization schemes that have been suggested or proposed. It ships with Linux. I think it has been shipping with Linux for 3 or 4 years already. And we do recommend the implementation of this particular algorithm, or even better, there's a double hash variant of this algorithm that has even better properties. It's easier to understand what this algorithm is doing if you look at this sample output of the algorithm. Basically, each of the columns is trying to show, for example, the first one or second one, the IP address and port number to which you are trying to connect. Then F, of course, is the result of the hash function. Min ephemeral and max ephemeral are two kernel variables that are supposed to allow the administrator to select the ephemeral port range to be used. We recommend, as you can see from here, the range from 1024 till well, 65K, right? This is something interesting to know because other than the specific algorithm that many systems were using to select the ephemeral ports, many of them were using an ephemeral port range that was really too small. For example, Windows was using a 4K port range, and many other systems were using at most something like 15K, whereas they could be using, as you may see, a much larger range. Then we have the counter. That's the global counter that was mentioned in the previous slide. And finally, the last column shows the port number that was eventually selected. So in the first two rows, you can see the first two connection attempts. You are trying to connect to the same IP address and TCP port, so the result of the hash function is in both cases 1000. So when you add the result of the hash function to the counter and to the min ephemeral variable that basically tries to put the port number within the ephemeral port range, you get port number 2024. In the second connection attempt, the result of the hash function is exactly the same because you are connecting to the same endpoint, and we assume, of course, that the secret key hasn't changed. So result of the hash function is the same. So when you add all those values, the only thing that has changed is the counter. So you can see that you get port numbers that belong to the same seconds, okay? In the third row, we are trying to connect to a different endpoint. The IP address has changed, and as a result, the result of the hash function has also changed. In this case, it's 4504. So when you add the result of the hash function, min ephemeral, and the counter variable, you get port number 5530. Fourth row, you try to connect to the same endpoint. The result of the hash function is the same, so you get port number 5531. And you can see that port numbers are incremental within their specific port number space, but they belong to different port spaces when you connect to different endpoints. So in the fifth row, you can see that we go back to trying to connect to the first system. Now, of course, the result of the hash function is the same, so we get a port number 2028 that belongs to the same seconds as in the first two connection attempts. So the idea here is that if, for example, the attacker was operating the machine 170.210 and so on, if he could cause the target system to establish connections with him, I mean, even then he wouldn't be able to predict the port numbers that would be used to connect to a different endpoint. So this is the reason for which I was saying when I was starting the discussion of port numbers, that it's not that you really want port randomization, but port obfuscation. I mean, for the connections that you get, or the connections that you use, the connection request that you send to a specific system, you don't really want those port numbers to be random. The point is that an off-path attacker shouldn't be able to predict the port numbers that will be used for connecting to other endpoints. And this is, I'm going to make like a side note here, because there was a very large router company that I'm not going to mention, that they were saying that they had produced this tool, or that they have a customer that they had this tool that was measuring the quality of the port randomization scheme that they were using. So for them, or for their customers, this algorithm was crap, because they were establishing connections to a specific system, and of course it looks like port numbers are not being randomized, but they are measuring the wrong parameter, because you don't care whether the port numbers that are used for the connections that you receive are random or not, but what you care is that an off-path attacker cannot predict the port numbers that are using. So they implemented this very complex machinery in their code, just so that this tool that their clients were using would provide the clients with the result that, well, the port randomization scheme that you are using is great, right? They even published a paper, and the IETF was just about to standardize that. So thank God this didn't move forward, but I think that they are still revising that paper. So let's move now to some discussion of the TCP window. Of course, the TCP window is using TCP for the flow control mechanism, and the TCP window can introduce an artificial limit in the data transfer rate that will depend from the window and the round trip time. So under ideal network conditions, for example, that there is no packet loss, in order to prevent that artificial limit from being imposed, you should set, or it's expected that you set the TCP window to twice the bandwidth delay product. Many systems, in order to avoid these artificial limits in the data transfer rate, they simply set the TCP window to a large value, so that they never get the data transfer rate limited. The problem is that there's no such a thing as a free lunch. So you cannot just increase the TCP window and that's it. Because when you increase the window, other than that of the flow control, the TCP window also determines which segments will be considered valid for that connection. So if you use a TCP window that is really large, and actually larger than necessary, you are also opening the door to attacks. If you pick like a really large window, say 65K or whatever, the attacker will have much better luck attacking you. So one of the things that we recommend in our document is that if you are using an application that does not really need high throughput, an example of this could be some kind of application for signaling voice over IP or whatever. Well, there's no need in using a TCP window that is large. Some of you may say, well, we could use one of those mechanisms for automatic tuning of the TCP window, but while I will not discuss those algorithms here, you may guess that they have their own security vulnerabilities inside. So the advice for the TCP window is don't use a large window unless you really need it. Let's now move on to the TCP urgent mechanism. Well, urgent flag and the urgent pointer. The TCP urgent mechanism is meant to provide a mechanism for an application to signal an interesting point in the data stream. Usually what happens is that, 5 minutes, when a specific point in the data stream is marked with the urgent pointer, the application will jump to that point and ignore all the data in between. This was traditionally used for Telnet and FTP and so on, right? However, most implementations implement the urgent mechanism for out-of-band data rather than for this of simply marking an interesting point in the data stream. And this of, what I mean with out-of-band data is that they put the data that are supposed to be urgent in a different queue than normal data. And not just that, but different implementations implement that out-of-band data mechanism in a different way. Virtually all stacks just keep a single byte to queue urgent data. So in the middle of this slide, you can see a possible sequence of bytes that are transferred to another system, and you can see two urgent indications, right? So if one of the, well, virtually all stack systems receive these two origin indications, and before reading the first one, the one marked with the number 3, a second origin indication is received, the second one will replace the first origin indication. So you can see that actually 1 byte of data has been lost there. Other stacks, I think it's the only one is Microsoft, implement what would be like true out-of-band data, because they support multiple bytes of out-of-band data. The only problem here is that they were not imposing any limits on the amount of data that they were queuing, so you guess what the possible results are, right? Another problem with the origin mechanism is that there is an ambiguity in what the semantics of the origin pointer are. As it happens with many other things, implementations differ from what the IETF says. So the IETF says, or was saying, that the origin pointer was pointing to the last byte of origin data, whereas most implementations make the origin pointer point to the byte following the last byte of origin data. And it's funny because many systems, at least all the ones that I have checked, they include a system-wide toggle to select which of these two behaviors you want, but they only affect how you set the origin pointer, but not how you process it. So if you actually set this flag in your system, you will end up with a system that cannot interoperate with itself. Okay? Just to add a little bit more to this mess, there are some middle boxes such as Cisco PICs that they clear the origin flag and set the origin pointer to 0 by default, which basically means that whenever there is one of these systems in between the two endpoints that are communicating, the origin data is not reliable anymore, because the origin indications are going to be clear from your packets. So this means that origin data is not reliable anymore in the current internet. Well, all these ambiguity issues, of course, make the task of, for example, network intrusion detection system much harder. Lots of things that could be processed in a different way. And also, if you consider that the origin indications are not reliable anymore, well, we went to the conclusion that applications should not rely on the origin mechanism. Thank God there are only a few applications left that actually make use of this. I think one of them is Microsoft SQL. I don't know what for, but they do it. So the advice is that you shouldn't rely on the TCP origin mechanism. It should just be used as a performance improvement. That is, in the event that the system really gets an origin indication, well, just use it as a performance improvement to jump to that point and avoid processing unnecessary data. And also, you should set the OOV inline socket option, so that instead of origin data being processed out of band, it's kept in band. Okay? We submitted a paper to the IETF on this subject. This paper, this internet draft, has already been accepted, so the IETF is going to recommend this stuff that I have mentioned here. TCP, yeah? Okay. I will provide just a brief discussion of some TCP options. Actually, only one, the TCP timestamps. TCP timestamps are used for measuring the round trip time and also for protection against wrapped sequence numbers. When it comes to protection against wrapped sequence numbers, you can think of TCP timestamps as an extension of TCP sequence numbers. And well, in this case, many systems, well, timestamps are required to be monotonically increasing in the same connection, but they are not required to be monotonically increasing across connections. Okay? Many systems were setting the timestamps from a global timer, global counter, which is good in some respect because you can perform an improved handling of SYN segments. Basically, the same type of thing that BSD systems have been doing with ISNs. There's a connection in the time wave state, you receive an incoming SYN, and if the timestamp that SYN has is larger than the one that you had seen, the connection is accepted. But of course, this leads also to predictable timestamps. Of course, this has security implications, and predictable TCP timestamps are undesirable. Some systems, such as OpenBSD, decided to introduce randomization for timestamps. This is the same thing that they did for ISNs, but this breaks the BSD hack of processing the timestamps or ISNs in incoming segments. So what we did is to provide an alternate algorithm for setting the timestamps. It's exactly the same thing as Steven Bellovin proposed for the ISNs, exactly the same thing that we did for randomization, but nobody cared about that. I think that the only people that were doing this was Linux. The standard is going to be revised, and we think that they are going to recommend this algorithm in the revision of RFC 1323. Should I jump this? Sorry? We have to go? Okay. Well, as a brief discussion, I'm not going to get into the details because we are out of time. Last year, or a couple of years ago, you may have heard about these vulnerabilities in TCP that were discovered by people from Outport 24. They were basically the NAFTA and FinWay 2 attacks. In our paper, we described the attacks and proposed countermeasures for them. I was providing here like a brief discussion of these attacks that I will jump. And finally, the final thing that I want to mention is that of TCP/IP stack fingerprinting. If you use the tools such as Nmap for TCP/IP stack fingerprinting, you know that they have an amazingly good precision of which operating system a remote system is using. What we did is try to come up with the proper way to respond to the proof segments that tools such as Nmap were sending. And we expect that in the next few years, if all the available implementations end up following our advice, the precision of these tools will be not as good as today. And just as conclusions, working on TCP and IPv4 security didn't have much glamour, in particular to do it in 2009. When we published our documents, I read reviews from many people that my idea was that they never went past to the preface of the document. Well, I guess that most reviews were based on the preface of the document. But still in 2009, there are lots of things to do, specifications to change, implementations to update. And I am aware of efforts at the vendor community, even in some router vendors, to test their stacks. And there's also work within the IETF to update the relevant specifications. We would really appreciate if, in particular, the people involved in TCP/IP hacking could send us feedback, because our idea is to update our document in response to the feedback that we get. So, thank you. Okay.
Thank you, Fernando. And we're going to break for lunch for 45 minutes. So that would make it what?